get started. The electric field worksheet is due on the 21st. Your web assignment is due on the 19th, and I changed it. Okay, so and again, I didn't upload all the assignments back into Canvas. So Canvas will say the 18th. Web assignment will say the 19th. Go by what it says on web assignment. And I'm going to. I probably won't get to. I will not complete the discussion on Gauss's law today, but I will get to some of it today. There's a worksheet associated with it. It's due on the 26th. And I will tell you off the bat, Gauss's law is very abstract. It's very strange. And the worksheet was designed, even though it's not an easy worksheet, to help you to better understand Gauss's law. Okay, and you're only really learning a portion of it. There's a lot more to Gauss's law. We can't learn all of it just because you need Calc 3. Okay, if you had Calc 3, maybe you'll probably understand it better. A couple things for my 8 o'clock class. I wrote some things on the board that weren't. I didn't give a full picture regarding what the battery does, and so I kind of wrote some notes here for you guys who are in the 8 o'clock class. So when we talk about the battery does work on the charges storing energy in the system. So it's kind of like when I lift an object up from point A to point B, I do work on the object, giving the potential energy. The battery does work on the charges, giving the potential energy. But the work done by the battery is basically the negative of the work done by the field. And so we write the work done by the field is negative delta U. The same thing happens when I lift an object between 2 points. So let me get a mark. So let me get to my eraser. If I lift an object from here to here, I do work to lift up the object. But the work done by the gravitational field is minus the change in potential energy. Because when I lift up the object, the work done by gravity is negative. The work that I do is positive. When I lift up the object, the work that I do goes into storing energy into the object. Does that make sense? So I wrote these down for you guys in the 8-10 class. Okay? Just so that, just to clarify what I said, because I didn't write this all out. And then the work done by the battery per unit charge, we call the electrical potential difference. And really, it's the work done by a battery per unit charge we call the volt. Okay, so I just wanted to mention that very quickly. Okay, so I want to do an example involving kinematics for a charged particle. And I also want to talk about field lines and then get into Gauss's law. But before I do that, I think I just want to see where you guys are at. I want to ask you actually, I have 2 questions to ask you. A poll question. So let me set up the poll in Zoom. And the question I want to ask, at least the first one, is this. So everybody see the poll question? And the poll itself. So go ahead and answer this question. You have the configuration of 3 charges, and you want to figure out what is the direction of the electric field at the position of the black dot, which is halfway between the positive and negative charge, halfway between the line joining the positive and negative charge on the base of the triangle. Okay, so I just need 2 more people to respond. Okay, so we're done, and I'm pretty much happy with everybody's response. So let me end the poll, and let me share the results. These are the choices people made. Most people chose D. So let me stop the share. And let me go to the board real quick. I drew the charge configuration, and then in blue, I drew the electric field lines due to each one of the charges at point P. Electric fields point towards a negative charge and away from a positive charge. So you have this guy pointing up, and then these 2 pointing to the left. So if you have 1 vector pointing up and then 2 vectors pointing to the left, the sum of these 2 will be somewhere in that direction. Although, yes, that's correct. And so the choice for this was D. The length that I drew here for the vectors are not indicative of the size of the field. I just connected the point to the charge. So the answer to that one was D. So let me do one more. So this one's a little bit more challenging. And you guys all see the poll. Okay, so go ahead. This time you have a line of charge, kind of like the first problem you're doing for the worksheet, and you want to set up the DE for the electric field produced by that charge contained within dx. You're just setting it up. By the way, point P is halfway along the length of the rod. Okay, so almost everyone has responded. Everyone's responded. So let me end the poll. And let me show the results. There's the results. We have a distribution of answers. So let's talk about this. Let me stop the share. Okay. So I drew the system on the board. And we need to, the DE, the equation for DE is K dq over r squared r hat. And I write r squared this way because it's really the magnitude of the vector that points from the source of the field to the point at which you're calculating the field. So this is a uniform charge distribution, so dq is basically q over L dx. So I'm going to put q over L dx here. And this problem wants the y component of the electric field. Okay. So let's write r hat over here. R hat points in this direction. So the x component would be cosine theta, the y component would be sine of theta. But sine of theta is going to be equal to opposite over whatever this distance is, we'll call r. So the y component is going to be k, q over L, times dx. And I'm going to write my a over r here. And then in the denominator, I just got to put the distance squared. Where the distance squared is going to be a squared plus x squared. So the correct answer was which one? It was A, right? This one matches A. So this is how you're going to set up when you do the worksheet. If you haven't done it yet, if you do the worksheet when you do the worksheet over the weekend, that's what you have to do. Yeah, and Chase, that's okay, right? You can choose either one as the angle. It's up to you, but you got to get the same answer. I mean, if you choose this angle, you would be calling this cosine, but then cosine is A over R, so that's fine. Yeah, it doesn't make a difference. Okay? All right, so what I'm going to do now then is go back to our kinematics discussion, and I just want to do a quick example. Let me switch my PowerPoints. Okay, so the other day when we left off, we talked about the motion of a charged particle in a uniform field. Uniform meaning its value is the same everywhere, and we're looking at time-independent fields. So from a time independency, we're just saying it's a constant with respect to time, and it's uniform over all space. Okay, and of course, if you have a uniform electric field, then A is going to have the same value everywhere. And using the language of kinematics, then we'd say the acceleration is constant. And we've done problems with physics 205, motion and constant acceleration. So the velocity is going to be acceleration times time plus the initial velocity, and then the position vector is 1/2 the acceleration times time squared plus the initial velocity times v plus the initial position. Okay, that's all that is. So whether you're doing electric field or gravitational field, the equation for motion and constant acceleration are the same. Just the letters change, because you have to change the letters because your acceleration is expressed in terms of the electric field. So let's do an example. So we have a particle of mass m. Its mass is 1.2 times 10 to the minus 8 kilograms. And it has a charge Q of 1 millicoulomb. Minus 1 millicoulomb. You have a homework problem similar to this, and you're given this initial velocity. You can use v naught or vi, whatever makes you happy. Okay, as 3I minus 5j, and I know I'm not being careful with the sig figs, times 10 to the third meters per second. And it enters a region space where the electric field is uniform and is given by minus 6I plus 2j times 10 to the fourth newtons per coulomb. Let's see. What is the acceleration? Well, the acceleration is going to be q times v over m. So q is going to be minus 1 times 10 to the minus 3. We put in the electric field vector. The coulombs will cancel when they divide by the mass. And your acceleration will turn out to be, let me get my notes. Once you do this on your calculator, (5i) minus 1.7j times 10 to the 7th meters per second squared. Does that seem like a big acceleration? That's a lot of g's. Okay, that's a lot of g's. But that's typical for small particles like electrons and things like that. What's the velocity after 3 seconds? Well, I just got to plug in t equals 3 seconds. So the velocity after 3 seconds is going to be this acceleration times 3 seconds. Oops.
Professor, it's 3 microseconds.
Oh, 3 microseconds, sorry. Thank you. Yeah, because 3 seconds, it would be relativistic. Thank you. Then I have to do relativity. No, that's okay. 3 times 10 to the minus 6 seconds. And then I got to put in the initial velocity. And then we use our calculator to work this all out. When you do it on your calculator, you get okay, 3.15 I minus 5.05 j times 10 to the third meters per second. You can see these problems aren't that hard if people have a hard time visualizing what's going on in these kind of problems. I mean, you just got to think of these as a projectile problem. That's all you got to do. So if you don't remember the projectile problems from Physics 205, you should go back and review them, because the physics is the same. You get a couple of homework problems that you actually have an electron that's a projectile. You use the equations for motion at constant acceleration. You look for our textbook, it was chapters 2 and 4. Okay. Let's find R. And again, I'm just going to plug in value. 1/2 the acceleration times the time, plus the initial velocity times t, plus R naught. And so all I got to do then is write down 1/2 this acceleration, and again, it's after 3 microseconds. Our time is 3 microseconds. I gotta square that. And hopefully I have a little space to write this down. The initial velocity was this value. And then the last term is my initial position. My initial position is 0. Actually, it wants a displacement. So it wants R minus R naught. So I'm going to take this guy and put it on the other side of the equation. And I get that. And then all I got to do again is just use my calculator. When I do this on my calculator, I get 9.22 I minus 15.1 J times 10 to the minus 3 meters. Now for a small particle, I mean for us this looks like a small distance, but for a small particle it's a pretty big distance. That's really all you do is if you want the change in kinetic energy, then you got to find the magnitude of this vector and the magnitude of this vector. You guys know how to do that. It's 1/2 mv final squared minus 1/2 mv initial squared. So this gives you the work done on the particle, because the work done equals the change in kinetic energy. Okay, so this, in a sense, is a review problem for you guys. It's a review of Physics 205. So, yeah, if you don't remember kinematics, please look at try to do a problem from kinematics. Okay, because you're going to see this you're going to see some kinematic problems every once in a while in this course. In this unit, and when we do magnetism. Okay, you can't remember, you can't forget that stuff. So. Okay, all right. So, I want to move on, and I want to start talking about the concept of electric field lines. And the reason I want to do this is because this is going to lead into our discussion of Gauss's law. Now, as you remember, the force on a charge, force on a test charge, is always directed along the line joining the test charge and the source of the field. And we establish the direction of the field by bringing a test charge in the vicinity of the source charge and investigating the force on a test charge. And then we divide it by the value of the test charge to assign a unique vector at each location in space that characterizes the condition produced by the source charge. And from a math perspective, we call it a field. If you can define a unique vector in every region of space, and it could be due to whatever disturbance that's causing it, that's called a vector field. In math, there's vector fields and scalar fields. As long as the vector is unique at that location in space, we call that a field, a vector field. Scalar field, you're assigning a unique number in every region of space. An example of that is assigning a value of temperature for every region of space. That would be called a scalar field. Okay. So for example, if I have a positive test charge, I can draw a bunch of arrows representing what the electric field would be at any location in space due to the due to the source charge you see in the figure given, the green charge that you see. those arrows represent the fields at those locations in space. The orange dots just indicate the location in space. If I have two charges, I can do the same thing. If I have two charges, let's say one is positive, one is negative, I can assign vectors to every location in space that's produced by those two charges. And so that picture shows that. Maybe let me make this picture larger. And I think at some point in your calculus courses, you've seen pictures like this. Now, if I connect, or if I draw tangent lines along the vectors in which a positive charge would experience that force, those are called lines of force. So let me write this down. Let's say I connect tangent lines along field vectors that indicate, I should just say vectors, that indicate the direction of force a positive test charge would experience. Then the lines that you get are called lines of force. Or electric field lines. Michael Faraday came up with an idea because he wanted to get an understanding of what this idea of the field is. He was very good in the lab, but he wasn't as good at math, and so he had to try to figure out ways to picture things. But this is an abstract topic. And so he came up with this idea of the field lines. So for example, let me show you the field lines due to a positive charge. So what I did in this picture, I took that original picture and drew yellow lines that connect the little vectors that I originally had drawn. Those yellow lines would represent the direction a positive charge would move in the vicinity of Q, based on where it's located at initially. Okay? So, if I put a positive test charge along any one of those yellow lines, the charge will move along one of those yellow lines. Questions on that? Okay. Now, if you notice, let me go back to that figure. If you notice something, if I draw a positive charge, and the field lines would draw like this, Let's say I draw an imaginary circle. In 3D, it would be a sphere around at some location R. We'll call it R1. And then I draw another sphere. Let's make it bigger. At some location R2. Remember, these are imaginary spheres. So, where's the field bigger? On the green, on the surface of the green sphere, or on the surface of the red sphere? Anybody? Yeah, the field's heavier. I mean, the field's greater anywhere along the surface of the red sphere. In fact, because the electric field is K Q over R squared, and because the circle has a constant radius, then the field has the same value all the way around that red circle. But what you notice is that the number of lines per unit area is greater on the red circle than on the green circle. The density of lines passing through the red circle is higher than the density of lines going through the green circle. And so the density of lines that we draw here represents how strong the field is. So we can use this idea of the density of lines when you look at field lines to get an idea of what the field is representing.
Aren't there like an infinite number of lines though? I mean, like I get that they like spread out as they go out, but like, is there like an infinite number?
Yeah, you're right. So what's the right number of lines to draw? That's your question, right? And yes, Chase, you can represent the field, the electric field, in terms of a wave, but these are static fields. It's easier to describe in terms of a traveling wave when you're talking about a time-varying field. So, yeah, you're right, and Vincent, you're right. There's I think that was Vincent, right? There are an infinite number of them, but we don't draw all of them. We draw what's representative of them. Isn't it true that if I double the charge, I would have twice the number of field lines would be double, right? If I double the charge, I only have twice the field. And so what I do is I draw twice the number of lines. If I draw 10 lines for this one, then for something that's twice the charge, I would draw 20 of them. So I don't have to draw every single one. Because what this picture does is gives me a representation of the field. It gives me a representation of what kind of force a charge will experience in the vicinity of these sources. Does that make sense?
Oh, so it's just like a convention that like if the charge is stronger, you draw more vector lines.
Yeah, you want to draw it in a way that reflects the size of the field. So if I double the charge, I want to double the number of lines. So there's some rules for drawing these. Okay, there's some rules. So I'm going to show you the rules. Number one, the number of lines leaving a charge or entering a charge is proportional to the charge. So there isn't just a specific number you have to draw. You can choose whatever you want. But if you have another charge that's twice as big, you have to draw twice as many lines. Because the electric field points away from the negative charge and towards a positive charge, then for a negative charge, the field lines leave it. For a positive charge, the electric field lines leave it. For a negative charge, they approach it. The field lines will either end on a charge or begin on a charge. Otherwise, they will go all the way to infinity. And of course, the density of lines that you draw is proportional to the size of the field. When you draw these pictures, the lines have to be drawn so that that reflect the symmetry of your system. You want to draw the line symmetrically, leaving or entering a point charge. And the last thing is the one that students have a hard time with, is that you cannot have two field lines cross. Okay, you cannot have two field lines going in two different directions. Because otherwise you don't have a field. A field, by definition, defines a unique vector at every location in space. If you have two vectors associated for a location in space, that's not a field. That's like friction. Friction is not a field because friction, the direction of the vector for friction at any location in space will depend on which path you take. Does that make sense? You can't say you can have a line that's pointing north and a line that's pointing east at the same time at a point in space. Then it's like saying I can go north and east at the same time. You can't do that, can you? You can't separately go in two separate directions at the same time. At least a single person. So you have to have your field is defined as unique at each point in space, so no two field lines can cross. So here's an example of the field lines. And this is not a picture that's drawn. Let me make this bigger. This is not a picture that's drawn. These are two positively charged conductors that are placed in oil, and there's threads inside the oil, and the threads form the shape of the field. The threads represent the field lines. Can you see that? In fact, the field lines kind of repel each other because both charges are positive. Now, this is not a ferrofluid. This is just charges. This has nothing to do with magnetism. This just has to do with charges. Okay, another example. These are two oppositely charged conductors. And this is called a dipole, by the way. I'm going to, when we get into chapter 25, when I have a little more time in lab, I'm going to talk a little bit more about the physics of dipole. And this is called a dipole that we talked about in the properties of charge lab. There's a lot of interesting physics. So you talk about dipoles in biology. So you can see the field lines. I mean, they match. I mean, what you see there, let me go back. They're basically the arrows that you see there connected by tangent lines. I didn't realize you covered stuff like this in biology. Okay. I can't show you this
To the
video.
ground?
Unfortunately, I can't show you that video because the sound will play, but the video will not play because I don't have a big enough computer. I don't have enough memory in my computer to make that run. Okay. If I were on campus, I wouldn't be running the camera. That I can make that video. But basically, that video was to show field lines. They had these two Van de Graaffs, and they would basically drop feathers in between them, and you would see the field lines produced by the falling feathers in between the Van de Graaffs. So let me say a few more things about these field lines. I'm going to draw a positive charge, and I always go with positive charge because that's the convention, I guess. We're going to do negative charge. And I'm going to draw some imaginary field line, imaginary circles. Let me draw this positive cube. Let me draw my field lines. Okay, that should be enough. to look at the idea of that the electric field is proportional to the number of lines per unit area. So let's consider the electric field along this surface of radius R1, and then the electric field along this bigger sphere of radius R2. Now, I'm interested in the number of lines per unit area, and I'm interested in the electric field. So let's take a look at the electric field at those two locations. So the electric field at location 1 is K Q over R1 squared. The electric field at R2 is K Q over R2 squared. Everybody's okay with that. And I'm not writing vectors, this is just the magnitude of the field. Okay, if you want me to be more precise, I can do this, I guess. So what I want to do is take the ratio of E2 over E1. What do I get if I take this divided by that? Well, I end up getting R1 squared over R2 squared. Okay, so now let's take a look at the number of lines per unit area going through this sphere. Remember, this is just an imaginary sphere I drew that's of radius R1. Remember, a few minutes ago we said that the number of field lines per unit area is indicative of the electric field. The number of lines per unit area is proportional to the electric field. Okay, it doesn't matter and I think what Vincent said, yeah, n is infinite. But we have to draw all of them. Okay, here I drew 1, 2, 3. How many did I draw? Like 8? So the number of lines per unit area is indicative of the electric field. And so I want to look at E1, which is proportional to n over A1. If you notice, the field lines go through both the red circle and the green circle. The same number of total field lines go through both of them. So what is this ratio? Well, it's the number of lines over the surface area of this sphere. Granted, I'm drawing in 2 dimensions, but you got to think in 3D. So that's a sphere. Okay? What's the surface area of a sphere? 4 pi R1 squared. Let's do the same thing for E2. E2 is proportional to n over A2. And that's equal to the number of lines that also pass through the green one over 4 pi R2 squared. What do you think I'm going to do? I'm going to take the ratio of E2 over E1. If I take that ratio, guess what I get? Why did I show you this? Because it shows you that this is a good idea for me to use to describe the electric field. Because I get the same relationship using something that we already know as this. So I get the same ratio. So this idea seems to work. That's why I went through that exercise. Does that make sense? This gives some plausibility to what I'm trying to picture here. I'm trying to use the field line to picture what's going on. Okay, so now that I've shown that this idea can work for us, let me try something else. need to erase my board here. It's messy. If E is proportional to N over A, then it's also true, I'll write this in a different color quickly. The number of lines passing through each one of those imaginary surfaces, and I say imaginary with emphasis because these are not real spheres, I'm just using them for trying to understand what's going on here, then it's true that N is proportional to E times A. Does that make sense? And so, whatever N is, it doesn't matter, whatever N is, there's probably some proportionality constant I'm missing, but I don't care. Okay? So, I want to find E times A for this sphere. Well, what's the electric field at this point? The electric field at this point is K cubed over R1 squared. What's that surface area? 4 pi R1 squared. What does this come out to be? It ends up being K cubed times 4 pi. So this says that N is proportional to K times Q times 4 pi. Now, there's another way to write K. K can also be written this way. One over 4 pi epsilon naught. Epsilon naught is the permittivity of free space. The permittivity in a vacuum, because all the problems we're doing right now, we're doing in a vacuum, okay? The ran most of this cut off. Oops, sorry. Thank you. That better? Maybe I'll do one more thing. Okay. All right. So I think you're just missing the pi or something. Thank goodness. Okay. So this represents, and we'll talk about more about it when we talk about capacitors in the next unit. This represents how well the field lines will penetrate a material. Okay. So I can write it in the following way. Now, let me do the same thing for the green sphere. If I do the calculation for the green sphere, well, then I'm going to do the electric field is K Q over 4. K Q over R2 squared times 4 pi R2 squared, and I'm going to get the same thing. 4 pi KQ, which is Q over epsilon naught. So as long as the charge is inside the sphere, I get that the field lines are proportional to whatever charge is enclosed inside the sphere. Now I've done it for this particular example. One can use vector calculus to show this is true in general. And so my goal here today is just to build up to that, but I will not do a rigorous proof in this course. Really, I have already done it. I've written down Gauss's law. That the number of field lines that pass through any one of these surfaces, closed surfaces, these are closed surfaces, is equal to, it's proportional to the charge enclosed. The number of field lines is proportional to the charge enclosed inside the closed surface. But let me say a few more things. Because I need to say something about this product, E times A. Okay, I need to say a few more things. I need to kind of build this up a little bit. And I want to do that because I hope that it makes this a little bit easier to understand. Okay. Questions? All right, let's continue. Okay, so again, the total number of field lines passing perpendicularly through the imaginary surface only depends on the amount of charge that's enclosed within the surface. Notice that these field lines are all passing perpendicular to the surface. If these lines had a component that was not perpendicular to the surface, the component that's not perpendicular to the surface, the component that's tangent to the surface, will not penetrate the surface. In my example, right here, I assume, well, not assume, but in my example here, the field along this imaginary surface had the same value because the field is kq over r. So anywhere along this surface or anywhere along this surface, the field had the same value. So this calculation was easy because the field had the same value anywhere along the surface. But what if the electric field is not the same along the surface? Then what? What if I have some kind of weird charge configuration where this guy here is not uniform over the entire area of the surface? It changes. Does the total number of lines mean going through the center or going through it? It's basically the number of lines going through the surface. They can go out of the surface or they can go into the surface. If the charge was negative, Jacob, then the field lines would be going into the surface towards the center. These would be pointing in the opposite direction if this was negative, because the field lines go toward the negative charge. Does that make sense? We're really looking at what's penetrating the surface. Okay, so if I have an electric field that varies across the surface, then I have a problem. I have to break up the electric field. I have to break up the surface into pieces that are small enough such that the electric field is constant over that surface. So that means I have to calculate a delta n for each surface that makes up, or each little surface that makes up the area. And then I can say the sum of my delta n's is my total number of lines. And that's proportional to the sum of the E sub i's, delta A sub i's. But I haven't been accurate in what I've written down, because what if you have a surface and the electric field points like this? Only the part of the electric field that's perpendicular to the surface penetrates the surface. The component that's tangent to the surface doesn't go. We're looking at the field lines that penetrate a surface here. And so I need a component of the electric field that's perpendicular to the surface. So I need to know the normal to the surface. And I need to know the component of the electric field normal to the surface. And so I need to change this. And I need to say, okay, I need the component of the electric field along the surface. With the dot product, I take the dot product of the electric field with the normal to the surface. And then I can say my delta n for one of these pieces is E dot the normal to the surface and delta A. And then I sum over all these to get the total number. I shouldn't have equal, I should say proportion. Sorry. So I break up the surface into as many pieces as I need and calculate the dot product of the electric field with the normal to the surface multiplied by my element of area in a small area, and then I sum over all the areas. And remember, only the component perpendicular to the surface passes the surface, not the component tangent. That's why we need to introduce that dot product. Okay? So my next question is this. What if the field varies continuously over the surface? Then what? What happens to all the stuff if the field varies continuously over the surface? What happens to my deltas? Well, my deltas become d's. My deltas become d's. These become deltas, d's. And again, I screwed up. I got to put proportionality. What does that become? You can't write it as a sum anymore, right? What does that become? You get an integral. Okay. Oops. Not too far. So if the field varies continuously over the surface, the number of field lines is proportional to the integral of E dot n dA. That integral is called the electric flux. The product of E times A is the electric flux. Whether it's written this way or as a summation or as an integral, this is the electric flux. Flux meaning it represents like an outward flow. In this case, the field line. But when you talk about water, it represents the flow of water through a surface. The math here that we're going to be doing here is very similar to the math you would do when you talk about thermal conductivity materials. And also, when we talk about circuits next week, when I do the more general description of the circuits, you're going to see some of this. Okay, in terms of when I talk about, not circuits, but when I talk about current. So the electric flux, I've written there three different ways. One if you have a constant field, one if you have a discretely varying field, and one if you have a continuously varying field. Guess which one works in every case? Right, the bottom one, the integral works in every case, whether E is constant or not. Okay, that's the most general description of writing the electric flux. It's the integral of E dot n dA. So that's the flux through a surface, the outward flow of the field lines through a surface. But generally, we are interested in the flux through a closed surface. Okay, the net flux through a closed surface represents the number of lines leaving the surface minus the number of lines entering the surface. If more lines leave than enter, then the flux is positive. If more lines enter than leave, then the flux is negative. When the surface is closed, the normal to the surface is always defined to be outward from the surface. That way, when you have a positive charge, the field lines are leaving the surface. Oh, that circle? You're asking about that circle? That's a good question, Brandon. When you put a closed circle on the integral sign, it means you're integrating over something that's closed. So in 2 dimensions, it's a closed surface, like the surface of a sphere. In 1 dimension, it would be a closed path. So in Calc 3, you will see that symbol. See, when I drew them before, let's go to the previous slide. Oops. Okay. This was for open surface, just any side of a box, for example. Okay. If I include all sides of the box, then I'd write a little circle on the integral sign. Okay. So let me say one couple more things about this. And I've added all this stuff in my discussion, and I'm hoping to making it a little bit easier to understand this, because a lot of times instructors don't talk about this, and I think it's kind of unclear, but we'll see. To help us understand a little bit more this idea of flux in general, consider a fluid of constant density flowing through a pipe. And I drew a weird pipe. Okay? I drew a weird pipe. And I made the left side and the right side different. And I want to only consider the fluid going through. I want to make the discussion a little bit easier. We can always have a fluid going through the lateral sides of the pipe, but then that complicates things. So I'm just going to look at fluid going from left to right. In a time delta t, how much fluid goes through the left-hand side of the pipe? How much fluid goes through A1? And how much fluid goes through A2 in a time delta t? Okay, so when you look at that picture, the reason why I'm using water flowing through a pipe, because a flux represents a flow of something. Field lines are a little bit weird because you're talking about the flow of field lines, but it's really the lines that are leaving or entering the surface. While fluid's a little bit more concrete. So let's consider the left-hand side. Let's consider a time delta t has elapsed. Okay? And I'm going to consider how much fluid has passed this area A1 in a time delta t. Well, if the fluid's moving on this side with some velocity v1, the volume of fluid that goes through here in a time delta t is going to be A times v1 times delta t. Okay. And if I multiply by the density, that's going to give you the mass of fluid that goes through the left side in this time period. Now I can do the same thing on this side and look at, the fluid's doing this, the water's going like this through the fluid. Okay. All right. And I should write the magnitude of this vector. But what about on this side? Well, in a time delta t, how much fluid goes through here? Well, remember, I have to consider the component of the velocity vector that's perpendicular to the surface. So I have to take a dot product of the velocity vector v2 here, dot the normal to whatever that surface is, times, and I should put a1 there, times a2 times delta t times the density. So what goes through this side is this value, what goes through this side is this value. If there is no drain in here, or if there's no water faucet in here, whatever comes inside here has to be equal to whatever goes out there. Isn't that true? The flux through this side has to equal the flux through this side if I have no drain in here, or if I don't have a water faucet in here, a source. And also, as long as these, of course, these have to be the same too, right? Well, they don't have to be the same, but let's make them the same just for simplicity. Let's let V1 equals V2 equals V for simplicity. They don't have to be the same. But then this will change. Okay. So I want to keep it simple. Let's make V1 and V2 the same. That way the rows are the same. And if that's the case, then if I look at what goes into the surface, which is negative, because the normal to this surface is that way, I have to define actually this to be negative, because the normal to the surface is this way, the velocity is this way. So really I have to define this as negative. That means whatever goes in is equal to whatever goes out. The n vector is the normal to the surface. It's the line that is perpendicular to the surface. Okay. Okay, so this is the total flux through. I'm ignoring the lateral sides, but it's possible you can have fluid going through the lateral sides. So what I've done is I've calculated the integral of the density times v dot n dA. And I said that this is 0 because there's no source, there's no water faucet inside the pipe. So whatever goes in has to be equal to whatever goes out. What goes in is considered negative, what goes out is considered positive. And I neglected to put the dot product here, but this has to be negative. I have to treat it as negative because the dot product between the normal to this surface and n is -1. And so what I've actually calculated is the net flux due to the mass flux you can think of, and I get 0. If I have a source in here, okay, if I have a source in here, this is the flow period of time. If I have a source in here, then this is not going to be 0. It's going to depend on the amount of mass that's flowing in or out of this thing. So this thing is going to represent the amount of mass flowing in or out. So if I have a source of water, I'm going to get more out of this side than I do on this side. That's because I have this source in there. If I have less going out than coming in, that means something's sucking up the water. That means this term is not 0. This accounts for what's being lost or gained. Well, when we do electric fields, we replace this with the electric field and the whole dMdt with your Q over E. And for fields, you replace rho times V with E. And you replace dm over dt with Q over epsilon naught. That's what you do. Now I have 3 more slides in there. I'm skipping in the interest of time. Those of you who are interested in Calc 3, you might want to look at them. Well, we really don't need it for our purposes. Okay, before we leave, I still got time, never mind. I want to do some examples of the electric flux. So let me write this general expression down for you. We've established it, not in general. I haven't been rigorous in what I've been saying because I can't. But we've established the fact that if you calculate the net flux through a surface, it's equal to the charge enclosed over epsilon naught. We can use the analogy with the water pipe, where we replace the mass going in or out of the water pipe, the rate at which mass is going in or out of the water pipe, with Q over epsilon naught, and this density times velocity with the electric field. It's the same thing. And so you say, this says that the integral of the electric field over a closed surface is equal to the total charge enclosed over epsilon naught. And this whole thing is proportional to the number of lines entering or leaving a surface. All this came from this idea of the field line. I wasn't rigorous in proving this. I kind of led to that. Okay, in Calc 3, your instructor might prove this for you. But I can't do it. So let's do this example. You have a point charge placed at the center of a ring having a linear charge density lambda and radius b. I want to calculate the total electric flux through spheres of radius r less than b and spheres r greater than b. You say, okay, well, let's figure out what we can do here. Here is my charge Q. And let me draw the ring. I'll draw it in red. I'll write down ring of charge because I'm not a bad artist. Okay, that's a ring of charge. And its charge density is lambda. I want to draw an imaginary sphere that encircles Q. So we have a sphere, imaginary sphere. Of radius r less than b. And I want to calculate that integral. Okay? They may say, okay, I got to calculate the electric field and then I got to integrate over this darn thing. But we already know the answer. Because this equation says that the integral of the electric field around a closed surface is equal to whatever charge is enclosed over epsilon naught. So my answer is that the electric flux denoted by the Greek letter phi sub e, is just Q over epsilon naught. And I should use small q. I don't have to do any calculation. That's what that means. So now if I draw another imaginary sphere that's giant, big giant sphere, where its radius is bigger than the radius of the ring, then phi is going to be easy to calculate. It's going to be whatever charge I've enclosed inside there. What's the charge of the ring? Well, it's the circumference of the ring's diameter greater than b, and I'm done. I don't have to do any calculus. Okay, because that integral says that the integral of the electric field over the surface is equal to the charge enclosed over epsilon naught. That's what that integral tells me. Let's do another one. Suppose I have a sphere, a solid sphere. And I haven't said, by the way, I haven't said this, that's Gauss Law. Suppose I have a solid sphere, or I'm sorry, not a solid sphere, just a spherical shell. Actually, it doesn't matter. And I have an electric field is uniform. It means it has the same value everywhere. And I want to calculate the flux through the left-hand side of the sphere. Boy, that's going to be hard because, the electric field is just E. Let's say it's in the x direction. Let's just say E can be written this way. But then the normal to the surface changes all the way around. For some reason I can't write. The normal to the surface changes all the way around the sphere. So I have to write an expression that represents the normal to the surface. I actually thought this was really hard to do, but it's actually not that hard to do. I did it. But I don't have to even do the integral. Why do I not have to do the integral? That's my question. Why do I have to do the integral? Why can't I do this problem? I can do this problem without evaluating the integral. I'll get my answer. Because I have to set up, I have to write an expression for n hat, and then I got to integrate over this darn left-hand surface to do it. And you can do it if you want to have fun. I mean, it's actually good practice for your calculus class, but you don't have to do it. Why not? Well, don't these field lines go through the entire sphere? You go from the left-hand side to the right-hand side. Whatever goes in equals whatever goes out. Isn't that true? There's no charge enclosed. There's no charge enclosed, so whatever goes in has to be equal to whatever goes out. This is 0. So whatever goes in on this side has to be equal to whatever goes through the center of this darn thing. So let me ask you, is the normal to the surface that goes through the great circle of the sphere in the same direction? In fact, the normal here always points towards the left. So the integral, if I just do the integral over this surface, I'm done. Well, this E dot n is constant. In fact, this integral becomes E, and then the area is the area of the great circle, right? It's just the area of the great circle. And I have a negative because these two vectors are in opposite directions. The normal goes that way, and the electric field goes this way because the field lines are entering from the left-hand side. That's it. That's my answer. I'm done. When I learned this material, when I took E&M, the first thing the instructor said is, where did I lose you? Because I know it's abstract. So let me say a few more things about this. And I know this stuff is abstract. This equation that we see here is Gauss's law. Okay? This is Gauss's law. So why is it useful? Why am I doing all this? Because it's actually one of the fundamental equations in E&M. It ends up being one of Maxwell's equations. It is a way of rewriting Coulomb's law. This law exists because Coulomb's law depends on 1 over r squared. If Coulomb's law did not depend on 1 over r squared, this would not exist. If we have systems where we have symmetry, we can use this equation to actually calculate the electric field. If we have systems where I can pull out this from the integration, I can solve for the electric field. And that's what we're going to use this for. For this course, we're going to use this form. This can be written a different way. For those of you at Cal 3, I think you know that you can write this a different way. When you write it in the other way, that form is much more useful. But of course, you need to know Cal 3. And then you have to learn how to solve a special type of differential equation that we're not going to cover here. Okay? Okay. What can you say? I'll just say one more thing and then I'll stop. What can you say about the number of flux lines through each surface? What can you say about the number of lines passing through each surface? No matter what the shape of the surface, the number of lines passing through the surface is the same. If you take the charge and put it outside the surface, then the total flux through any one of those surfaces is 0. Okay. So I'm going to stop here. You guys have any questions on the homework? Number 9D. Okay, I'll do number 9D. Let me go through 9D. Let me take a sip of water first, and I'll do 9D. Okay. Well, I'm hoping, Jacob, that if I do number 9D, maybe that'll help you a little bit more. I don't want to go through, I mean, I would hope I don't want to go through every single part, but I can talk about it. So this is, to me, what I would call applications of integral calculus, okay, which is something you cover in Math 32. So in 9D, we have a solid sphere. Radius A. And your density, your charge density is rho naught e to the minus r over a. You want to calculate Q. You want to derive an expression for Q, and then you want to derive an expression for rho naught. So, we have a density that's not constant. One of the problems that students have, okay, and you have to unlearn this. No matter what you do, you have to unlearn this. You take high school physical science and you learn, density is mass over volume. That's only true when? When is that only true? If it's uniform. Otherwise, we have to do this. Okay? So we're looking at that case. And that's such a hard thing for people to remember, to understand that this is only true, and then mass. This is only true if this number is the same value over the entire volume. Otherwise, m is equal to the integral of rho dv. And so that's one of the things that gets in the way of students learning this material, is they're so stuck on this. And it's not true. It's only true if it's uniform. Okay? So you have to get away from that. That's one thing that gets in this way. So, if I have a solid sphere and the density varies, but the density varies only with distance from the center of the sphere. That means if I have a sphere and the center is a solid sphere, if I consider a spherical shell, I mean, just imagine you have an onion. An onion essentially is the shape of a sphere, right, Chase? Let's pretend we have an onion that's perfectly spherically shaped. But the onion has a lot of layers, correct? Let's have a special onion that has an infinite number of layers, that has this density. Then, everywhere along this surface, this number is going to be the same. Anywhere along the surface, this number is going to be the same. And so the amount of charge I have anywhere along this is going to be rho times my element of volume. So that's going to be rho naught e to the minus r over a times my dv. What is the volume of this sphere that's thickness dr and radius r? Well, dv is going to be the surface area times the thickness. Surface area times thickness gives you the volume. So then, my total charge Q is going to be the integral over all these spheres. And that'll give you Q. That's part A. Is that okay? Chase and Jacob? Wait, you're saying what is that or what is R hat? There is no R hat in here, right? Because we're calculating a scalar, we're not calculating a vector. The goal of this exercise is to just learn how to set up dq. You're not calculating the electric field in any part of number 9. You're just calculating R hat. I'm sorry. You're calculating dq. Okay?
Professor?
Yes.
So, it's really small, but what is the convention for whenever we go from little q to capital Q?
There's no convention. I mean, I call it big Q.
Okay.
Because I call it big Q in the problem, right?
Yeah, it was just we started with D and then lowercase q. That's why I was wondering.
Yeah, I should have probably, I was being sloppy. If it bothered you, I should probably run with this.
Okay, I was just making sure that there wasn't a change in convention.
I apologize. I messed up. I mean, big Q is the total charge, but I mean, I will usually write D little q for the infinitesimal, but really I should write D big Q because otherwise, like, okay, well, why did I switch signs or why did I switch symbols? And so you're right in pointing that out. So I apologize for that. What is A naught? A naught is the radius. A naught is the radius of. Oh, I'm sorry. I messed up. I'll tell you why I put A naught. Okay. Because this represents the charge distribution on an electron in an atom. And A naught is the radius of the electron. And so, I'm thinking of the radius of the atom. That's why I put A naught. So I apologize for that. So there shouldn't be an A naught. Okay. It's just the radius of the sphere. But realistically, where I got this from, where I got this charge density, it comes from the charge density of the electron in the hydrogen atom. Okay, so Chase, yeah, I mean, I guess you have to. I think what they want you to do in part A is just to round the answer off to 3 decimal places. But then, when you do subsequent calculations, you want to keep extra digits. That's typically what you do. I mean, when you do subsequent calculations, you always keep the extra digits. So, Jacob, you said, what do we use for R? What do I use for that? It's given in the problem, right? It's in my case, it's 9.88 centimeters. A is the actual value, right? A is the actual radius, is the number. R is the variable I'm integrating over. Yeah, you have to integrate it by parts twice. So if R equals A, then this ratio is 1, right? Right, Jacob? If R equals A, this ratio is 1. Okay. We get A over A. Okay, so part B says, not part B, but the second part of part B says, well, what if you know this number? Can you solve for this? Yeah, but okay, Chase. I mean, um, all I said was R equals A, and so if this is the actual radius of the sphere. What R and A, big R and little a? Yeah, they're different. Big R is the actual radius of the sphere. Little r is the variable you're integrating over. You can't make all the r's the same, right? When you're integrating, you can't make this r and this the same. You have to differentiate them. You have to tell the difference between one is a number and the other is a variable. Correct, because big R is A, and you're given the number for A in the problem. Okay, I mean, you can do this, okay, and substitute A and then substitute again what the value of A is. It doesn't matter. It's just a number. When I say big R equals A and I show you the value, that's the final number you're going to integrate to. Because you're integrating this from little r equals 0 to little r equals A, which is equal to big R. Right, because what you put here is whatever the values are at the extremes. Right, that's what you do typically when you integrate. These are the extreme values, or the limits of this variable. Correct, just a number, right? And they specify the number in the problem. The number is specified. It should be in red in your problem. All right, when you look at WebAssign, the number is given in red. That's a constant. Okay, that's fine. If it's 1 centimeter, that's fine. So, the second part is like, given this, can you solve for this? Yeah, that's a good question, Aiden. Do you have to convert to meters? And yeah, I think you do, because when you integrate, you're going to have r's in your equation, right? If you just have the r's in the exponent, you don't have to. But when you integrate this, there's r's outside of the exponent, then you have to. Right? I forget. I can't tell you off the top of my head what this integral is. Actually, if you do use sub once, I think you should be able to get this, right? No, you don't. You have to do integration by parts. Yeah, if the integral has some polynomial in it, yeah, you have to do the conversion at the result of the integral. But if you just had this exponential, you didn't have to, because of the ratio. Okay. So, yeah, so for the last part, just put a number here and solve for this. The second part of that question, all you got to do is solve for rho naught. Only for the first part you have to do an integral. So, Jacob, can I pick another one? Because you said all the parts. Can I pick a different one? Do you want me to look at a different one for this particular problem? It would be hard for me to do every single part. But I think if you've done a couple of them, then you get the idea. Okay, I'll do C. So I hope, Jacob, I hope that's okay, right? I just do C. Okay, let me look at C and then I'll look at number 11. Because I got asked to do C. Okay, and C, you have a charged disk. By the way, when you do this with mass or you do this with density, it's the same problem. Okay. Okay, so I'm going to take, this is a charged disk. The density, this is a surface density. I'm going to give you my expression. I know it's weird, okay? And just so I can vary this for everybody. So this is kind of a weird distribution. Now remember, in the previous problem, I broke up the sphere into layers of an onion. This time, I'm going to break this into tree rings. Imagine I have a very, very old tree. Okay? And old trees have a lot of rings. Let's pretend that this tree was around since the beginning of the universe. So it has a lot of rings. And so what I'm going to do is I'm going to break this up into a lot of rings. Of thickness dr. Okay? If I take a pair of scissors, okay, maybe if I use a special cutter, and I cut this all the way around, I get a piece like this. Let's say the radius is some arbitrary r, and the thickness is dr. What's the length of this piece? Well, it's the circumference of that circle. And the area of this thing is 2 pi r dr. The amount of charge on this thing is going to be my area times this thing. Okay, I'm going to be careful with my notation. And I know I apologize for my sloppiness sometimes. And so then this is going to be my charge density times that. And then Q is the integral from 0 over to whatever the radius is. Can you guys see that okay? Is it too light? I'll press harder. Okay, so that's all you have to do. The purpose of this exercise is to get you to figure out how I can break up something so I can write a dq. Now you did something similar to this when you did gravitation in 205. I don't know if you did all the shapes, but so now you can come up with this integral. If you know what Q is, you can solve for sigma. Oh, that's mine. And this is my density. Yours are going to be different, Jacob. Yours will be some other expression. Because if you notice that the exponent's in red, right? The exponent in your equation is red. Yeah, you have to, right? That's my point. My point of what I said earlier is that you kind of have to get away from this idea that, for example, mass is equal to density times volume or density times area. You can't do that because it's different. It's each piece that makes up this thing has a different density. You have to integrate. Okay? It has to be part of the integral. I mean, if you think about it, each one of these pieces, if I make R bigger, there's a different amount of charge on it. And then I have to add up every piece. Now, how do you add them up? I have to integrate. Yeah, because this is R to the 19 times R is actually 1. Oh, okay. Maybe I misunderstood your question. I'm sorry. I was wondering why you had to integrate. Sorry. And then sigma, I'll write it in black, is going to be your total charge divided by this integral. Which, this is an easy integral. The other one, yeah, the other one you can probably look at about Wolfram. But this one you can do easily, because this is R to the 21st over 21. So. Yeah, sorry, Jacob, I misunderstood your question. And so the other one was number 11. Number 11. And let me draw it on the other board. I have two equal charges. Let's do here. Let's do here. I want to find the electric field at this point. This is D. This is 2D. I think I need more colors. Okay. It's 45 degrees. I want to find the field there. Due to this charge and this charge. Okay, so so the field due to sorry, I'm dropping things. The field due to Q, right? At this point points this way, and the field due to this guy points this way. We're getting the height to be just d over 2. Well, this has to be d over 2. This has to be d over 2. And so yeah, this has to be d over 2. Okay, so let's work through this. Let's calculate the field due to this guy. Okay, let's calculate the field due to this guy at this point. That's going to be U1 is equal to K times Q over D squared in the I hat direction. The field due to the other one is going to be K Q over D squared. Oh, not D squared. It's going to be this distance. And the cosine that look okay? Now, what does this come out to be? What does this denominator come out to be? Okay, so let's simplify this a little bit. This is going to come up here. And this 2 is going to cancel out these 2's. And so I'm going to get and so then I got to add this to this. So my y component is fine. And so E total, which I'm running out of space, hold on a second. Sorry, I keep stepping up in the cord here. There's going to be this guy plus this guy. You should get that. It's easy to make algebra errors. Oh, you're right, d squared. It's not the square root. I messed up. Sorry about that. You're right, Jacob. I messed up. But that's the final answer. We okay with that? I think Aiden asked that one. I couldn't see the. Yes. Because that whole thing was in the denominator, right? This whole thing was in the denominator, so this has to go back up here. Because it was like this, right? Well, what is the cosine of 45? What's cosine of 45? What's the sine of 45? Okay. Are we okay then? Okay. No other questions? So I'm going to end it then. You guys, okay. So you guys have a good weekend.